Hello everyone, welcome to 15.4. We're talking about polar integrals, and in this video I'm going to talk about how we set up a bunch of polar integrals, and then I think I'm going to do one more video where we convert Cartesian integrals to polar integrals. So it'll be I think a pretty quick two-part video on this chapter. And so polar integrals, we've seen polar coordinates before, introduced them briefly in 14.2 when we're talking about limits. And yeah, polar integrals here, they're very important because we'll see them a lot from here on out. There are other types of integrals which use polar integrals, and so it's important that you know what's going on in this section. So to get started, let's just jump into two very quick problems. I'm going to do 15.4 number 1 and 15.4 number 2 just right off the bat, just so we can set up some integrals, and then we can see what's going on. So I should have probably done this before starting the video, but whatever. Okay, so 15.4 number 1. So what are we doing here? We're going to be given a sketch of a region, okay, and like this, and we want to set up the associated polar integral with that region. So here, then this right here is actually 9, and this right here is also 9. So how do we figure out what our limits of integration are going to be? So when we set up a region, right? So here it is, and we want to describe the region in terms of area. So from the previous chapter, we learned that area is equal to this, right? It's equal to double integral over the region of dA. And I said that dA was equal to dx dy or dy dx, right? Well, in polar, this is in Cartesian. In polar, dA is equal to r dr d theta. And what does that mean? Well, r is essentially your radius, or how far are you from the origin, right? So these guys are going to be r. So you can have tick marks along the r. And then d theta is going to be the angle, right? So in this case, this will be theta counterclockwise from the positive x-axis. So if we had this line in the bottom left as our r, then that would be our theta, and it looks like something around like 5 pi over 4 radians in this case, okay? So this is what we're dealing with when we're talking about r dr d theta. And how do we set up our limits? Well, in this problem, it's going to be some double integral of r dr d theta, right? We're setting up polar integrals. And what is r? Well, if we look at r in our region, right, we start at the origin, and the origin is inside the region, and then we keep on going, we hit the circle, right? We hit that circle. And what is that circle? Well, if we go along the x-axis, we see that we hit 9, right? Which tells me that the radius is going to be 9 there, and a circle is every point that's equidistant from a fixed point. And in our case, our fixed point is going to be at origin. So along the boundary of this 3/4 circle here, right? Along this boundary of this 3/4 circle, the radius is always going to be 9. So in our case, then, our radius is going to go from 0 when we're at the origin. Okay, when we're at the origin, our radius is 0. And then when we go out along and we hit the boundary, we go up and hit 9. So we go from 0 to 9. Okay? All right, and now what is theta? Well, d theta, our region starts along the positive y-axis here first, right? And we go along the circle, and we circle all the way back over to the positive x-axis. So we're going from pi over 2, right? Because the positive y-axis, the angle that it forms is pi over 2, all the way over to the positive x-axis, where the angle is going to be 2 pi, right? So when we go from pi over 2, we go to 2 pi. Pi over 2 into the x-axis, which is 2 pi. And that's going to be our integral, okay? And that's going to be the bounds of my integral, and this integral right here will give me the area of this 3/4 circle. Make sense? All right, let's do another one real quick. 15.4.2. And what is it now? So now I have this. I have a tiny circle on the inside, and then I got a bigger circle on the outside, and it's the area in between them, right? And this guy appears 4, this guy appears 1, this is 4, this is also 1. All right, so in similar fashion, we set up our bounds, r, dr, d theta, and a lot of people are like, oh, can we integrate d theta before we integrate dr? Remember, I emphasized heavily that the outside integral is always going to be a constant, and d theta, the angle of our like region essentially that we rotate between, usually always ends up being constants. So d theta is r dr d theta is going to be how you integrate these integrals like 99.9% of the time. I actually can't think of an example off the top of my head where you do not do r dr d theta. So that aside, let's set up then our region. So when you do polar integrals, again, you just take a ray from the origin, right, through your region, and you look at what it hits. So for r, you see, where do I hit the region? Well, 0 is not in my region, so I have to go along, and then I hit the inside circle first, which looks like it's a circle radius 1, so that would be r equals 1, right? And then I go along this red line, and then I'm inside the region, and then when I leave the region, I hit the circle with radius 4 on the outside. So my upper bound for r is going to be 4. And then let's look at d theta. Well, d theta, we start here, right, in the negative y-axis direction. And so you can say this is 3 pi over 2, but it's probably better to say this is negative pi over 2 because you want to end up here, which is positive pi over 2, right? Because our ray would sweep, if we draw rays through our region, it sweeps all those angles, right? So that's theta. And then down here, right, your theta would be negative pi over 2, which is actually that guy. So our region then for theta is going to go from negative pi over 2 to pi over 2. So you start, wrong color, you start at the negative y-axis, and then we shade it all the way up to the positive y-axis, okay? And one last example, a little more complex than these first two. Let's look at 15.4.28. So what is this problem? We want to find the area of the region that lies inside the cardioid. R equals 1 plus cosine theta, and outside the circle, r equals 1. So we want to draw a picture of what this actually looks like. And so here's my xy axis, xy. So what is r equals 1? Well, r equals 1 is, remember what r is? R is going to be, well, not r, but if we square it, we get r squared is equal to 1, right? If we square both sides. And remember what r squared is. R squared was x squared plus y squared, right? Because in polar coordinates, x equals r cosine theta, y equals r sine theta. Go back to the polar coordinates limits video if you don't remember this, but that's the substitution we make, right? And so x squared plus y squared equals r squared, which equals 1. And so this is a circle of radius 1, okay? So radius 1, and then we get a circle. All right. And now we want to do this cardioid, r equals 1 plus cosine theta. So how does this work? Well, now if we want to look at r equals 1 plus cosine theta, essentially what we want to do is feed in values of theta and see what values of r is. So for example, what if theta equals 0? Well, if theta is 0, then I'm along the positive x-axis, right? And to plug that in, it becomes r is equal to 1 plus cosine of 0, which is 1, so r equals 2, right? And so then I'm going to be 2 units out, right? That green dot right there, right, at theta equals 0. And now let's do theta at pi over 2, right? Well, then that's 1 plus cosine of pi, cosine of pi over 2, which is 0. So 1 plus 0 is 1. And then that means I'm going to be here, right? And then pi over negative pi over 2, right? That's also r is equal to 1 plus 0, so that's going to be 1. Okay. And where else? Well, you might want to plug in other points like pi over 4. Okay, and then so that's r equals 1 plus root 2 over 2. So 1 plus root 2 over 2, that's like 1.7-ish. Okay, so along this line, right, this is pi over 4, right, this green dotted line right here, pi over 4, you want to go about 1.7 units out. So the circle is going to be 1 unit, and then you want to go, that's like 2 units, so you'll be like right here. Okay, and then likewise, let's say negative pi over 4, you'll get 1 minus, or also 1 plus root 2 over 2, which is 1.7. So here's negative pi over 4. All right, and then you want to go, not here, that's 1 unit, that's 2 units, and so you want to go like somewhere right there. Okay, and this is a cardioid. If you want to actually see the graph of this region better than what I can draw it, it's on page 902 of Godzilla. And yeah, so if you connect the dots, it looks like this. It's called a cardioid because it looks like a heart-shaped thingy. All right, so there you go. And so our region is lies inside the cardioid and outside of the circle. So it's going to be outside of the blue, but inside of the green, and that's going to be all of that guy. All right. So how do we set up this integral? Well, it's going to be a double integral of r dr d theta, right? That's going to be our region. And let's do it down here. So area is equal to the double integral of r dr d theta. What are my limits of r? Well, the problem actually gives it away from me, right? Because it says it's outside, or it's inside the region 1 plus cosine theta, and it's outside r equals 1. So again, if we look at even this, if we look at rays, right, through our region, it's outside of r equals 1, and it's inside of r equals 1 plus cosine theta. So from the problem even, I could say, oh, r equals 1 is going to be my inside bound, and r equals 1 plus cosine theta is going to be my outside bound, because, again, the region is squished in between those guys, okay? And this picture makes it very clear. So the lower bound is 1, and the upper bound is 1 plus cosine theta. And now the harder thing to do then is to figure out what the theta bounds are. But I guess you guys can kind of figure out what's going on, right? Because if I go very close to the y-axis, you'll see that there's still going to be like a little area in here that's going to be my region. So essentially what happens then is, yeah, I actually go from this guy down here all the way over to this guy, the positive y-axis up here. So I'm going to go from negative pi over 2 to pi over 2. And if you look at the red area in my picture, you'll see that, yeah, it gets smaller. The area gets smaller and smaller as I approach either the positive or the negative y-axis, but there's still going to be a countable amount of area until I actually get to that axis. So, and another way to see it is, oh, my region is in the positive x area plane, right? It's only in this positive x area region right here. And when you only have we're only in the right half of the xy plane, that's another way you can tell that your bounds are going to be from negative pi over 2 to pi over 2. All right. And so this actually gives me the area, so let's actually do this integral for once, just to finish out this problem and see how it goes. So like usual, it's like any other double integral. This becomes r squared over 2 evaluated from 1 plus cosine theta to 1, all right? And then this actually gets kind of annoying. But what you get is you get 1 plus 2 cosine theta plus cosine squared theta over 2 minus 1 over 2, all right? So that's what happens when you expand and you evaluate the integral. And now you still got d theta here. I forgot d theta there. All right, and so the 1/2 and the positive 1/2 and the negative 1/2 cancel out here, right? Because you got a 1 over 2 on the left-hand side, and then you got a negative 1/2. So you're left with then the integral from negative pi over 2 to pi over 2 of 2 cosine theta plus cosine squared theta. Yeah, so 2 cosine theta plus cosine squared theta over 2, and then over 2, but let's move the 1/2 out in front. Okay, cool. And now what? All right, now it's easy to integrate 2 cosine theta. We all know how to do that. Cosine squared theta is a little harder to integrate. So this is where you have to bring back some trig identities. Okay, and how do we bring back trig identity? Which trig identity do I need to bring back? Well, you have cosine squared theta is equal to 1 plus cosine 2 theta over 2, if you guys remember that one. The other one that comes up a lot is sine squared theta is 1 minus cosine 2 theta over 2. All right, so these guys are just trig identities that you need to remember. And so this is going to be 1/2 the integral from pi over 2 to negative pi over 2 of 2 cosine theta plus 1 minus cosine 2 theta over 2. All right, and now what am I going to do? So this is now 1/2. So I'm actually going to do something interesting here, and hopefully you guys will follow. But if you notice that this cardioid is symmetric, right? This cardioid is going to be symmetric along the positive x-axis. Like if I take this region in the top half, right? This region in the top half, it's going to be 2 times the region in the top half, right? So if I do 2 times area of top half, I'll get the area of the bottom half. And so the area of the top half, then, I can just take my theta integral, and I can go from 0 to pi over 2 and double that. And so that's just nice because then I don't have to calculate this negative pi over 2 integral. So again, so in the integral form, then this becomes 1/2 times 2 of from 0 to pi over 2, right? Again, from this picture, if I go from 0 to pi over 2, I take this top half right here, and then I just need to double that. So that's why it's 2 times the integral from 0 to pi over 2. And then I get, of course, the inside stays unchanged. All right, and that's another neat trick you should do for area integrals, is that see if you can split things up into quarters, even eighths, or halves, and then you only need to take a little slice of it, and it could make the integral a lot easier. All right, so again, for areas, see if you can split them up in halves or quarters, and then multiply that quarter area or that half area by the amount necessary to get you the entire thing. Okay? So here we go. So that cancels out the front, actually. So now I just got 0 from pi over 2, 2 cosine theta. I know this is just a lot of rewriting the same shit over and over. Apologize for that, but we'll get moving. Okay? And now, okay, so now we integrate each guy. And so this becomes the integral from 0 to, no more integrals. This becomes 2, negative, or positive 2 sine theta, all right, from 0 to pi over 2. All right, and then you got a plus 1/2. So then plus a 1/2 theta from 0 to pi over 2. And then I got a minus, all right, so this is cosine 2 theta over 2, but that, if you integrate, that's actually sine 2 theta over 4, right? Because if you take the derivative, this 2 has to come out in front, and then that cancels out the bottom by a factor of 2. So now I got to take that guy going from pi over 2 to 0. All right, and what is this equal to? This first guy, I'm going to get 2. The second guy, I'm going to get plus pi over 2, or pi over 4, because it's 1/2 times pi over 2. And then this guy is actually 0, because sine of 2 pi, sine of 2 theta, where theta is pi over 2, that's going to be sine of pi, that's 0. And then sine of 0 is going to be 0, so it's going to be 0 minus 0. So you get a minus 0 there. And yeah, so we get our answer for our area, which is 2 over pi over 4. And again, the important things we did, we split the region up into 2. We did this trig sub right here, and we set up the bounds of integration correctly, and this is the correct answer to our problem. Okay, so this was then setting up polar integrals in chapter 15.4. In the next video, I'm going to do a quick example of changing the bounds of changing from Cartesian to polar integrals, and we'll also do a kind of tricky setup as well in that problem. So see you guys in the next video.